Hi there. Welcome to the forces and free body diagram simulation. Here you will learn the type of forces acting on an object and understand how to make free body diagrams. In this simulation we will study several objects and the forces acting on them and define their motion. Click Continue to start with your mission. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you are playing a Labster simulation? Perfect, then let's get started with your first mission. Find the lockers and open one of them. Raise your lab pad for more. Find a lab coat inside the locker and pick it up to put it on. You're at the entrance of an engineering lab. Before you can gain access to the lab and all the other exciting facilities, we need to ensure that you have a proper understanding of some basic concepts in physics. Understanding forces and the motion of objects is vital in many aspects of science and engineering, ranging from your basic safety while in these facilities, all the way through to performing high-quality work in our projects. I'm having an issue, so I'll cut right to the chase. I'm having difficulties hovering at a defined height. Every time I'm at rest, as I am now, I struggle to stay in place. I'm afraid one of my motors isn't working properly, and gravity is pushing me down. It all started when I replaced some aluminum parts with titanium ones. Luckily for me, both you and Sir Isaac Newton are here. I hope you'll be able to solve my problem together. Locate Sir Isaac Newton standing next to the wall display. Click on him to have a chat.
Hello there. A few centuries ago, I expressed 3 laws that allowed for the study of how forces affect the motion of objects and systems. Assuming that you are an object that can be idealized as a single point mass, I am the expert at identifying what forces are required to make that object float. I am hoping that our friend here will be of assistance because nothing works better than 2 great minds combined. Dr. 1, do you know whether your motors apply force to your body when it's at rest?
Yes, I do. There is a lifting force that allows me to fly higher and lower whenever I wish to do so. This is the force I use when I am at rest, like now, to hover in one place.
Let's keep it simple. Since you're having trouble staying in one place and you feel weak maintaining your height, let's figure out what is pushing you down and what's keeping you up. Which direction of displacement is relevant to Dr. 1's problem with floating at a certain height? That's right. Dr. 1 is interested in staying at a certain height. Therefore, we should take into consideration what affects her motion in the vertical direction.
Click the button of the wall display to draw the forces. Make sure you are standing in front of the hollow table for a better view of the wall screen.
Dr. 1 requires one more piece of information from you. How much force do your motors apply to your body when at rest?
The lifting force I was always using when I am at rest is 30 newtons.
The lifting force comes from the power of the motors Dr. 1 has in her engine. Since this force requires contact between objects, it is called a contact force. But let's talk about me for a bit. Apart from being my name, Newton is also the SI unit of force. 1 Newton is equal to 1 kilogram meters per second squared. Dr. 1, we also need to know the mass of your structure.
It used to be 3 kilograms, but now, with the titanium parts, it went up to 4 kilograms.
Using the mass of Dr. 1's body, equal to 4 kilograms, you can determine the weight. The weight of a body is also called the force of gravity, and it is a force that does not need contact between objects to exist. Since the acceleration of gravity is approximately g equals 10 meters per second squared, and the force of gravity Fgi is equal to mass times g, with how much force is Earth pulling Dr. 1 now? You did the calculations correctly, using the right equation. 10 meters per second squared times 4 kilograms equals 40 newtons.
Click the button of the wall display to assign the magnitude on the forces.
Let's put things into perspective. In order to stay in one place, we should ensure that the sum of all forces is equal, meaning you're neither being pushed nor pulled. But as I see it, if you continue using your motors only up to 30 newtons, then your weight will always be pulling you down.
Click the button of the wall display to derive the net forces exerted. Good job, mate. By performing simple steps, we determine the net force applied to my body. The net force is symbolized with the letters sigma F and proves that I have 10 newtons pushing me downwards everywhere I go. I now know not to make changes in the material of my spare parts without doing the simple steps described in the free body diagrams methodology. These 10 newtons are applied to the center of my mass, or center of gravity. In a uniform field, like the one we experience in this lab, these 2 points match. You may easily visualize my body as a point when creating free body diagrams for the external forces exerted to me, but other objects that are not round and solid may be harder to visualize as such. Hover over the items on the bench to your right. Raise your lab pad to continue. Did you notice the images that popped up when you hovered your cursor over the apple and the coffee cup? Great. It was not easy to cut to the core of a cup full of coffee, but I did it to demonstrate that the center of mass is located at the core of such objects. I bet you're looking at all the objects around you now trying to identify their center of mass. Is the center of gravity assigned at the right place for the following bodies? That's right, only bodies A and B are correct. For object C, the center of mass should move to the left, and in object D it should move to the right. Where is the center of gravity, and where is the center of mass of Dr. 1? You have everything figured out regarding the center of mass and gravity. If I had a knife, I could cut my body through the middle to demonstrate where the vector of my weight originates. But I don't really want to do that. Do you know what else would be fun? I don't always fly. Sometimes I enjoy going skiing, or snorkeling, and other extreme sports such as bungee jumping. It would be great to understand the forces applied to my mass during these activities. We can use the hollow table to simulate all my hobbies. I hope you have fun while identifying the forces applied to my mass. Click on the spring button on the hollow table. Fantastic. Now identify which forces are exerted on the mass on the spring from the floating screen to the right side of the hollow table. Great. Now change the magnitude of the forces to move the mass downwards. Click the red button when you're ready. Good job. What you see here is a free body diagram of a mass on a spring. We used arrows to symbolize the forces on the vertical direction. In the direction of the motion, if the restoring force is larger than the weight, then the net force, sigma F, is pointing upwards and the mass will move up. If the restoring force is 100 newtons and the ball weighs 80 newtons, what is the net force and in which direction? Remember, you have access to a calculator at the top corner of the lab pad. That's right. To determine the net force in one direction, you should sum up all the forces in that direction. In our case, sigma F equals the restore force minus the weight, which equals 20 newtons. Click on the underwater button on the hollow table. Select the forces exerted on the submerged mass from the floating screen. You got it. Now change the magnitude of the forces to bring the mass to the surface. You rock. Great work understanding the creation of free body diagrams. It doesn't matter if a mass is at the top of a mountain or the bottom of the sea, forces that are exerted on it should be presented like this to solve any problems regarding its motion. Now the net force is pointing upwards and the mass is free to travel to the surface. Click on the wedge button on the hollow table. Select the forces exerted on the mass on the wedge from the floating screen. You did well so far. A mass rolling on the wedge reminds me of myself skiing at the slopes of Alps last winter. Why is the normal force relevant to the problem? That's correct. In order to experience the normal force, two objects should be in contact. If this force wasn't there, then you would have higher chances to reach the core of Earth, simple by standing. As you may noticed on the wedge, the normal force is the only perpendicular force to the inclined surface, since this force should be directed perpendicular to the surfaces in contact. Increase the friction. Click the red button when you are done. I hope you didn't expect to see any changes in the motion. Increasing friction will not move the mass upwards. As friction is opposing the motion, the only thing you achieved was to make it harder to roll down the wedge even if the other forces are increased. This condition differentiates forces that cause motion from those that prevent motion. Decreasing which force would result in the object sliding down the incline? No, this is incorrect. Please try again. Check out the Theory tab on your lab pad if you don't know the answer. That's right. By decreasing the friction, the weight of the ball can accelerate it down the ramp.
You have done a great job so far. You have seen how forces affect the motion of an object, and you can identify the contact forces. Plus, even though we assume that every mass is a point, you know where the center of a mass is placed in a random body.
Now that you've become an expert in forces and free body diagrams, let's see how you handle a real problem. In order to navigate through the lab, I don't only move vertically. That's why I have two motors that may apply forces in various directions. I will demonstrate this to you on the large wall display, and together we will figure out which direction I would move. At the moment, there are three forces applied to my body. The forces from the two motors, M1 and M2, and my weight. Remember to lower your lab pad to observe the wall display as we speak. According to the methodology for the creation of free body diagrams, the first step would be to break down angled forces to horizontal and vertical components. Notice the coordinates at the bottom right corner of the wall display. At the moment, the force applied from my second motor is at 60° angle from the horizontal axis. During this step, the force from the second motor is broken down into vertical and horizontal components. We should use the letters X and Y to symbolize the direction of each component. The trigonometric functions on the Media tab will help you make some basic calculations. You can always check the image on the Media tab to recall the forces from the motors. Which forces should you take into account when breaking forces down into a horizontal direction? That's right. The weight only causes motion in the vertical direction. Therefore, it should not be part of the analysis in the horizontal direction. As you see from the equations on the wall, 10 newtons are applied to the center of my mass on the horizontal direction pointing to the left. This is the net force on the x-axis.
Would you like Dr. 1 to demonstrate how to derive the net force in the vertical direction?
The two net forces that are shown on the wall display, one in the vertical and one in the horizontal direction, govern my motion. These net forces are a combination of the forces applied from my two motors and my weight. Given the final outcome, there is only one way I could go. It is impressive to see that even if no forces are actually pointing towards the exact direction of the movement, I am still able to move diagonally. Of course, I could have them both pointing in that direction, but there is no fun in that, is there? Use the left and right arrows on the wall display to repeat the steps of the process. Raise your lab pad to continue. Do you want to go through the process once more? I want to ensure you get the right take-home message from the motor problem. Once we have drawn an accurate free body diagram, we can apply Newton's first law if the body is in equilibrium or Newton's second law if the body is accelerating. But even though Sir Isaac Newton is sitting here with us, we should play the Newton's laws of motion simulation if we want to know more. The last exercise was important to understand how forces applied in multiple directions affect the motion of a body, as we did at the very beginning. For example, my issue with vertical flying has nothing to do with the air blowing sideways from the open window. You have successfully passed the introductory course covering drone and flying machinery navigation. You did this by learning how to create free body diagrams and understanding how forces affect the motion of a body. You are ready to go and explore more virtual simulations where you can navigate rovers, spacecraft, and racing cars. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.